Hi. So the goal for this video is to go over note set 3 in vibrations. I'm going out of town, so I wanted to make two videos splitting the note set in half. The first video being about springs, a little bit more in detail about them, and the second video being on pendulums or an introduction to them. And for this video, we're going to focus on springs. And so far in class, what we've talked about is the idea of a mass that is attached to a spring. And if I were to pull on the mass and then let go, it would start to oscillate back and forth about some equilibrium point. And the question is, what is that equilibrium point? Well, when it's horizontal, like we see here, we will just say that the equilibrium point is when the spring is not deflected. So zero deflection equals the equilibrium point, or let's say a horizontal system like this one. I'll say zero deflection specifically of the spring. Because yes, the mass is located at that position too if it's not moving. But for understanding, remember that the spring is what is essentially determining how much energy the system has. If we were to give some initial deflection, we have this potential energy storage that will then be converted to kinetic. So it's important to understand what this equilibrium point is. So for horizontal, it makes sense. Now, if we were to go to vertical, where we now include gravity, that's where things get a little bit more interesting. So let's look at a vertical system where instead of having a mass move right and left, let's assume that I have a spring that I will ultimately attach a mass to that will cause it to go up and down. Now, if I do not attach a mass to the spring, I just hang a spring, there's nothing attached to it. This location here is what we'll say is our equilibrium for the spring. That is just the spring hanging out without any mass attached. That is its natural state. Now, of course, if I stretch it or I pull on it or I work to compress it, it will want to come back to that equilibrium position as we already mentioned in class. But now let's say that, okay, let's attach a mass to it. And if I attach a mass to it, and remember, we're going to have gravity here. If I attach a mass to it, that mass will cause a force on the spring to cause it to elongate. So let's go ahead and draw that picture now. I have the same spring, except now I have included this mass at the bottom. Let's just have better. Where I have this mass at the bottom that has caused the spring to elongate by some amount. I will call this delta, a capital delta, the triangle. This is the deflection due to the mass. So this is some deflection due to the mass. Because of gravity. Gravity is going to pull down on the mass, so therefore we're going to cause it to elongate. And let's say that we have no forces, there's no initial conditions. It's literally just comparing this system now that we've included a mass. So assuming no motion, let's sum the forces. And we know it's not moving, we'll say that that's equal to 0. So if we draw a free body diagram on the mass, we know that its weight is going down, and the spring, who is now deflected, will have some force pulling up on it that is kx, where x in this situation is that amount delta that the mass caused. So depending on what your coordinate system is, we'll end up seeing that mg and k delta are pointing in opposite directions. So we'll see that mg is equal to k delta because of the mass being present. We have this initial deflection. We can see that that deflection will end up being based on the mass, gravity, and the stiffness of the spring. So let's keep this in mind for a second. Now, with this occurring, again, this is kind of like a new equilibrium for the system, because now the mass is on. Its new equilibrium will be referenced to, let's say, this position here, where that is going to be my new x equals 0, because of the fact that the mass will now oscillate about that position. If I were to move the mass or hit it with something to provide some initial condition, it will cause the system to move. So let's say now I have the same exact system. Let's see how well I can do with copy and pasting this. Let's see how much I get out of this. Actually, that wasn't terrible, as bad as I was expecting. I do want to move this a little bit this way. Now, let's go ahead and say that we're now going to cause this thing to move. So from the original position of the spring, remember that was here, we have now caused the deflection delta and some additional deflection x based on some initial condition. I have caused this thing to move. It's now going to oscillate. And I'm going to reference everything to that initial point of the spring. So what this means is that if I were to draw a free body diagram for this, I will have mg pointing down, and what's my spring force that's going to be pointing up if it's deflected some additional amount x? Well, it's going to be k times delta plus x, and that is now pointing up. And remember, this thing is accelerating, so if we sum forces now, we will have to set that equal to ma, or mx double dot. So if I were to sum the forces and set that equal to mx double dot, let's go ahead and assume that the positive x direction is down. And again, that's kind of arbitrary. You can define it however you'd like. But if I'm assuming that it's moving in that direction in this point in time, I would rather say that that's positive, so we don't end up with some weird signs popping up, because we're assuming that it's moving in the direction that is positive. So the acceleration would be in that same direction. So if we do this, we'll have mg, that's pointing in the positive x direction, minus k delta plus x is equal to mx double dot. And if we do some algebra, we will get the following if I distribute the negative k. Now, earlier, we just showed that mg is equal to k delta. That initial deflection is based on the mass and gravity. So that means that this term and this term, when you subtract them from each other, equals 0. And we end up getting the same differential equation that we already got in class, despite the fact that we included gravity in this example. Now, the moral, why I care about proving this, is that for systems under gravity, or experiencing gravity, if we, I don't say if, let's say for systems under gravity, we can neglect gravity if the equilibrium point is measured or is located at the way I want to word this is that instead of saying that this is the equilibrium point of the spring, because that's where the spring was completely undeflected, neglecting gravitational effects on the spring itself. That's where the equilibrium point would be. If we say that that's our equilibrium point, we have to include gravity in our analysis. But if I say that this location is my equilibrium point, where I've now considered that additional delta, I do not need to include gravity in my analysis. It all depends on where that equilibrium point, that reference point, is. So for systems under gravity, we can neglect gravity if, not is, can't spell, if the equilibrium point is located at, let's say, the mass, not at the undeflected spring location. This is the big picture here to see, okay, if I just hang this spring vertically, it's going to be hanging out with some equilibrium position. If I pull on it, it's going to want to come back to normal. However, if I attach a mass to it, that will assume is there forever. We're not going to disconnect it. We will say that this is the new normal. This equilibrium position is where we will oscillate about, where we include already that K delta force, that extra deflection delta is already included. So if we included gravity, we have to include that K delta as well. If we don't include gravity, meaning I just say it's just this, I just have Kx going up, we will end up with the same results. And it's an important one. It helps simplify problems significantly if we neglect the fact that the gravity caused some initial deflection of the spring already. That is part one of this video. Part two, or rather, that was the first part on spring. The second part on springs is understanding the parallel and series combination of springs. And I want to relate this to circuits, which I know is not a mechanical engineer's best friend, but the relationships between the mechanical domain and the electrical domain are so important that it's good to demonstrate them and show them. So what I want to do is look at basically what we do with energy and relate it to, let's make this nicer, and relate it to the two different domains. So if I look at, let's say I look at a resistor in the electrical domain. What does a resistor do with energy? Well, it dissipates it. We dissipate the energy through a resistor. In the mechanical domain, we haven't talked about this yet, but in general, in the mechanical domain, we'll have some sort of damping, which might be something like air resistance, for example. The word resistance is in that. This is why resistor and resistance are essentially the same, where we see that we're dissipating energy. Potential energy in the mechanical domain is stored within a spring. We've already talked about that. The idea that if I were to compress a spring, it has potential to move. That is a form of potential energy. In the electrical domain, the component that stores potential energy is a capacitor. Those both store potential energy. And lastly, if we look at kinetic energy in the mechanical domain, a mass stores kinetic energy. In the electrical domain, that would be the equivalent of an inductor. And what's really interesting is that if you were to do a circuit that contains some of these parts and then draw a mechanical system with those same types of parts but with mechanical elements connected properly, you will end up deriving the same exact form of a differential equation. The math works out the same for both domains, which is pretty incredible. And let me show you an example why. So if I have a capacitor versus a spring, the force of a spring is equal to K times X. Now, just some quick definitions. We're going to call a force something that causes something else to happen. You know, it's causing movement, it's causing things that occur. This is what we call an effort. It is putting effort in order to get things to happen. The position is some form of what we call flow. Now, this isn't exactly flow. This is something like a flow. We'll explain the differences later. But the idea that there's causing some movement, the movement itself is related to what we call a flow variable. So we have an effort variable and a flow variable. And the relationship between them is given by some sort of impedance. So what we will call the K, this is some sort of impedance. Now, if you were to go to the electrical domain, it turns out that there's a relationship that the charge on a capacitor, remember that capacitors are these two plates that have a voltage drop between them. There's a charge built up on the plates. The relationship between them is to say that the voltage, which I will give a little subscript electrical or elect, just so we can differentiate the domains, this ends up being equal to some charge on the plate divided by the capacitor or the capacitance. This is like an effort. Without the voltage, we can't get current to flow. This is like a flow, kind of. And then C is related to the impedance. Again, I'll put this in quotes because it's not exactly the impedance, but it's related to the impedance. And we can kind of see they're of the similar form. If you think about the fact that I have blue is equal to something in green times red, I can say that the K is something like, not, I don't want to say it's proportional to or anything like that, because they're not equal, but it's related to 1 over C electrical. And because of this relationship, where we see that this stiffness, this K, the spring constant, is related to 1 over capacitance in some way, we define a 1 over C term in the mechanical domain because of that match. This C term, this is called the compliance of the spring. If something is compliant, it bends to you. It's something that you have power over. So if you were to have a spring and it's really compliant, it's really easy to tell it what to do, bend or stretch or elongate or whatever. Like, you can control it because it's compliant. Now, if it's stiff, the issue is now it's harder to compress or it's harder to pull. So the relationship between these is that K, the stiffness, is equal to 1 over the compliance. Again, note that this does not have an electrical subscript on it. This is not the capacitance. This is a new definition of something that we call the compliance. By definition, this is the same as 1 over the stiffness. 1 over K is equal to C, or 1 over C is equal to K, however you want to think about it. But they are reciprocals of each other. The benefit is that we can draw electrical circuits representing mechanical problems. Where if we want to represent the spring in an electrical circuit, we can use a capacitor to represent it. And the capacitance of that capacitor will be based on the compliance C. Just like up here, if I had a capacitor that's given by some CLF, in the mechanical domain, we can draw a capacitor, quote unquote capacitor, considering that they are equivalent, mathematically speaking. We can then model that spring as a compliance in a circuit. And we'll see what I mean more by that shortly. So that's our motivation here. So with that motivation, we have to go ahead and understand how to combine impedances. So let's talk about what an impedance is. If we think back to circuits, we know that V is equal to IR. And I'm going to write it as RI, just to be in tune with my equations earlier. This V is an effort. I is a flow. Now, before I said that Q is kind of like a flow, because by definition, I is the derivative of Q with respect to time. So they are related, but they're related through a derivative. That's why I said this is kind of like a flow. Similarly, in the mechanical domain, X is kind of like a flow, while what do you think the actual flow variable is? If the flow variable for the electrical domain is current, which is Q dot, what do you think the flow is in the mechanical domain? That'll be velocity. Now, the reason that it's important to define efforts and flows is that if I were to do an effort divided by a flow, that will give me an impedance, which again is why up here I said it's kind of an impedance, because it is relating effort to something like a flow variable, but it's not exactly a flow variable. In this situation here, if I solve for V over I or any sort of effort over flow, that will give me an impedance. And typically we will say an impedance is not given by the letter R. This is a very specific case, we will say that an impedance is given by a letter Z, where Z is the impedance of the system. Now, the reason I care about impedances is because if I were to have impedances in series, let's say I have some Z1, which can be a resistor, it can be capacitors, or whatever they are, some sort of circuit component that provides an impedance. If you think back to your circuits class, if I wanted to combine these, I would say an equivalent impedance is Z1 plus Z2 when they're in series. And you can look at my notes. I think I have a lot more instances about why this is true. But I'm going to skip that for now. I just want to remind you of these equations. The other situation is that if I give you two impedances in parallel, in this situation, you have a voltage drop that is equivalent for both impedances. So we have the same voltage drop, the same effort, with different currents, right? Because the current's going to come in here and then split between the two with different currents, which is the same as saying different flows. In this example up here within series, they had the same flow because the current's going to be going through all of them the same, but they'll have different voltage drops or different effort drops between them. I'm hoping this is kind of review the idea of combining different impedances. If we think about the impedances in parallel, let's say I have a total I coming in with an I1 and an I2 splitting between them. I can write that I is equal to I1 plus I2. And I know that I is related to the voltage drop divided by the impedance, right? If I come back up here, I know that V is equal to IR or V is equal to IZ. If I were to solve for I, it would be V over Z. So the total I we will write as being the overall voltage divided by the equivalent impedance that it sees. I1 is going to be the same voltage because the voltage drop across things in parallel are the same. And the same is true for the second impedance, where the voltage drop is the same across both of them. We'll do V over Z2. We end up seeing that an equivalent impedance is given by 1 over Z1 plus 1 over Z2. Or rather, 1 over the equivalent is given by this. And this is our relationship for impedances in parallel. And a simple way to think about this, if you have two impedances, two specifically, in parallel, we can say that the equivalent is the product of the impedances over the sum. And you can get that just from combining fractions. If you wanted to do that yourself on paper, feel free. That doesn't work for more than two, but for two, that's a really good start. So in general, impedances in series share the same flow, and impedances in parallel share the same effort. So at this point, let's go ahead and look at an example of a mechanical system where I say we have a mass that is hanging by two springs. Let's say that this is K1, and let's say that this is K2. If I were to pull down on the mass, I want you to ask yourselves, do these springs share the same flow? Which is velocity. And if you want to think about it in more simple terms, you can think about it as displacement. Or do they share the same effort, meaning the same force? So think about that for a second. If I pull down the mass, are they going to have the same displacement slash velocity or the same force happening through them? Well, in this situation, assuming that these springs are different, I have K1 and K2, the force that it feels is going to be Kx. So the left one will feel K1x, the right one will feel K2x, which means they do not share the same effort. These two share the same velocity, which means that if I think about the springs as being impedances, I would draw those impedances as being in series. So in the electrical domain, what I would draw is something like this, where I have these two capacitors that are in series. Remember, springs are capacitors because they both store potential energy. And as I mentioned earlier, if I come back up to here, we see that the only way I can represent it in the circuit is if I use a term that's equivalent to capacitance, which is the compliance of the spring. So this K1 has some compliance, which is 1 over C1. And this K2 has some compliance that's related to 1 over C2. And again, we'll say that, there's some voltage source here, which is basically some force that is causing this thing to occur that the springs are feeling. Now, if I wanted to go ahead and try to combine these impedances, the question is, how do I do that? So I have these two impedances in series. How do I combine them? Well, the equivalent impedance is the sum of the impedances. But reminder, these are capacitors. They are not resistors. They don't add the same way because the impedance of a capacitor is not just C, it's 1 over J omega C. That is the impedance of a capacitor. Reminder that the impedances of a resistor is just R. That's why we're able to do that math a little bit easier with resistors. But with capacitors, it's 1 over J omega C. So if I wanted to add these up, I would have to say that ZEQ is going to be 1 over J omega C1 plus 1 over J omega C2. And that ZEQ will just be 1 over J omega some equivalent compliance. If I cancel out all the J omegas, I get 1 over CEQ is equal to 1 over C1 plus 1 over C2. This, by definition, is going to be the equivalent stiffness. This, by definition, is the stiffness of the first one. And this, by definition, is the stiffness of the second. The moral is that springs that are in parallel, mechanically in parallel, like we see here, these are mechanically parallel, they will add together. Now that might be confusing because it's circuits, and I know we don't like circuits. Let's do this from a free body diagram perspective. If I have a mass that, let's say, has moved down some amount x, thinking about this picture, I now have k1x pointing up and k2x pointing up. And we already proven that gravity doesn't matter if we're neglecting that initial deflection. So this is the positive x direction. If I sum the forces, and set it equal to mx double dot, I will get k1x going in the negative direction minus k2x is equal to mx double dot. I'll just get everything on one side. And if I were to subtract, or rather if I were to factor out the x, we can see that this is like some k equivalent, mx double dot plus kx. So the sum of them ends up being the same as an equivalent stiffness. So if I were to have two springs, I buy two springs, this one is 10, this one is 5 newtons per meter for both of them. If I bought a 15 Newton per meter spring, the response of the mass would be the same because the stiffnesses are the same. Now, if we look at springs in series, mechanically in series, what that would look like is you have a spring, and then a mass. And these springs are awful. Just like tension in a rope, if you were to pull on it, the force through both springs is the same. They have the same effort. So springs that are mechanically in series end up being electrically in parallel. Again, if we think about the flow as being velocity, because these are different stiffnesses, they may be deflecting at different amounts and having different displacements and velocities. Because of that, that's conceptually equivalent to each of them experiencing a different current as they were modeled as capacitors. So this again would be some compliance C1, some compliance C2. If we were to go through all the motions similar to what we just did, we would end up seeing that 1 over K equivalent ends up being similar to resistors in parallel. And we can write that KEQ is the product over the sum. Let's do an example where I ask you to find the equivalent stiffness of the system below. I'll give you some mass. This is K1, which I'm saying is 2 newtons per meter. Now maybe I'll write it in terms of variables first. K1, K2, and K3. K1 is 2, K2 is 3, K3 is 5. So these two here, these are mechanically in parallel. If the mass is causing them to stretch, they are sharing the same exact flow, which means that electrically they are in series, which is very weird to think about, but they are electrically in series. From what we discussed earlier, we see that if they're electrically in series, to find their equivalents, we just add them together. So if I were to add those two together, this is still K1 is equal to 2. This is going to be K2 plus K3, which is 8. Now, if I want to go further, I have these two springs that are in series. These are mechanically in series. They are sharing the same effort. The same force is being felt by these springs, or being felt by these springs. I can't speak today. As I just showed, we can find the equivalent of them based on the reciprocal nature of the stiffness. So I'll say 1 over K equivalent will be 1 over 2 plus 1 over 8, which we can do in our calculator if we want, or we can go ahead and actually just use fractions. 1/2 is 4/8 plus 1/8, that is 5/8. So that means that KEQ will be the reciprocal of that is 8 over 5, which ends up being 1.6 newtons per meter. So I can have a bunch of stiffnesses in a system that we can combine depending on if they're in parallel or series. When we get to lumped element modeling in a couple of weeks, we will see why understanding how things combine in parallel or series and how we can model them, how important that will end up becoming. But to summarize, we first went through the idea of gravity not really having an impact if we assume our equilibrium point is where the mass is attached. But once we go to parallel and series combinations of springs, we can relate them to the electrical domain. There is a relationship that is very similar, where if you look at efforts and flows, we end up seeing that the stiffness is kind of like a capacitor, except because they're on opposite sides of the fraction bar based on these equations that we have up here that come from the math or from the mechanical domain and the electrical domain. We are motivated to define a new variable, which is the compliance, which is the reciprocal of the stiffness. So if the compliance goes up, meaning it's much easier to bend it or to stretch it, that means that the stiffness has to go down. They have an inversely proportional relationship. And we just did a little bit of circuit review here to show what happens with different impedances. But what we learn is that for springs that are sharing the same flow, which is what they are in this picture, electrically speaking, they're sharing the same velocity here. That means that they are electrically in series or mechanically in parallel. This will get confusing. I want you to really take the time to absorb this because it is fairly complicated. We can prove that when they are mechanically in parallel, we can add the stiffnesses together to give us an equivalent stiffness, which I demonstrated here with the idea of if I wanted to represent this system, I can go ahead and just use one spring with the sum of them, and that will be good enough. And the one in series is a little bit different. We see that they share the same effort. Again, if I'm pulling on this down, we're going to assume that the force throughout this whole thing is equivalent. So each of those springs experiences the same force. But because they have different stiffnesses, they will not experience the same displacement. Thinking from an electrical perspective, if they do not share the same flow, that means that current must be different for both of them, which is what we see when we model them electrically in parallel. So in this final example here, we just showed that if we have things in parallel, mechanically speaking, we will add them together. And then if they are mechanically in series, like they are here, we will go ahead and do the reciprocal type of addition. We can also just say that KEQ is product over sum, which will end up giving us the same answer that we get from the fractions. It's really your choice what you'd rather do. I hope this makes sense. If it doesn't, please let me know. It's going to be a complicated topic, but we'll get through it together. Just keep trying and keep reaching out to me and we'll get through it. Okay. Thank you guys. Bye.